The air in Green Bank, West Virginia, on April 8, 1960, crackled not just with the hum of electronics, but with an almost unbearable anticipation. Deep within the National Radio Astronomy Observatory, a young, visionary scientist named Frank Drake was about to embark on a journey that would redefine humanity's place in the cosmos. His brainchild, Project Ozma, was not merely an academic exercise. It was the world's very first modern experiment dedicated to the audacious search for extraterrestrial intelligence. Its purpose was singular: to listen for any whisper, any deliberate broadcast, from a civilization beyond our own. Drake and his small, intensely focused team had aimed their powerful 85-foot radio telescope, a marvel of mid-century engineering, towards two relatively nearby stars, Epsilon Eridani and Tau Ceti. These stellar neighbors, at distances of 10.5 and 11.9 light-years respectively, were chosen because they resembled our own Sun, offering the tantalizing possibility of hosting planets capable of sustaining life. For days, the quiet hum of the machinery was the only soundtrack, punctuated by the rhythmic thrum of the Earth turning and the faint, natural radio noise of the galaxy. Then, at one point, with their receiver meticulously tuned to a specific frequency, a jolt of pure exhilaration shot through the control room. The pen on the chart recorder, a device tirelessly documenting the faint radio signals from across the vast emptiness, began to dance with an unmistakable rhythm. This was no random cosmic static, no fleeting anomaly from a distant nebula or a burst from our own Sun. What it captured, aimed directly at the star Tau Ceti, was a powerful, pulsating signal, perfectly regular and undeniably artificial-looking. It was a precise, repeated series of pulses, each arriving with the clockwork precision of a finely tuned instrument, unlike anything a natural astronomical phenomenon could produce. The discovery was immediate, profound, and utterly overwhelming. For decades, the true nature of this moment, its raw intensity, would remain a closely guarded secret, locked away from the public eye due to its immensely sensitive implications. Drake and his colleagues were seized by a controlled euphoria. They meticulously analyzed the technical readouts, examining the perfect square waves etched onto the recording paper, the precise timing of each pulse. Every instinct, every scientific shred of evidence pointed towards a singular, breathtaking conclusion. They had just intercepted a message from another civilization. This was it, they believed, the most monumental discovery in human history. Drake's personal logbooks from that period, now declassified and offering an intimate glimpse into those electrifying hours, reveal a fascinating transition. The initial excitement, almost a giddiness at the precipice of such a grand revelation, slowly, methodically, gave way to the cold, hard process of scientific skepticism. The team, rigorously trained to doubt even their most exciting findings, began a frantic, systematic search for any possible terrestrial origin for the signal. Could it be an overlooked local interference, a piece of their own equipment malfunctioning, a distant aircraft? Every conceivable Earth-bound source was investigated, every hypothesis pursued with a relentless, almost desperate determination. They needed to rule out every single possibility before daring to announce such an extraordinary claim to the world. The truth, however, when it finally emerged, proved to be a revelation far more telling than any alien message could have been. The perfectly regular, artificial-looking pulses, the source of such intense scientific excitement and hushed speculation, were ultimately traced not to the distant star Tau Ceti, but to a secret, high-altitude military experiment right here on Earth. It was a clandestine part of the Cold War's desperate technological race, a signal from a powerful, unannounced project whose existence was unknown to the astronomers listening to the sky. This astounding turn of events, a story buried for so long, establishes a core theme that resonates throughout the entire search for extraterrestrial life, a theme far more complex than the simple question, "Are aliens out there?" Instead, it frames the profound challenge of distinguishing a genuine cosmic signal from the vast, ever-growing cacophony of our own technological civilization. The search for extraterrestrial intelligence, it turns out, is first and foremost a deep, challenging, and often humbling exercise in understanding ourselves and the immense amount of noise we, as a species, generate across our own planet and into the cosmos. After the thrilling, yet ultimately humbling, realization that the cosmos is filled not just with distant stars, but with the echoes of our own terrestrial ingenuity, a new, far more profound question emerges. What if we do hear it? What if, amidst the ceaseless static and the faint whispers of a universe brimming with natural phenomena, we detect an undeniable message, a signal so precise, so mathematically intricate, that its artificial origin is beyond dispute? The true challenge, then, shifts from mere identification to something far more daunting: comprehension. How could we possibly decode a language born from a completely alien biology, shaped by an unknown history, and expressed through concepts utterly foreign to our own existence? Consider for a moment the intellectual Everest humanity conquered in the 19th century, the deciphering of Egyptian hieroglyphs. For nearly 1,400 years, since the decline of the Roman Empire, the ancient script of the pharaohs had remained an impenetrable enigma, a beautiful but silent testament to a lost civilization. Thousands upon thousands of inscriptions covered temples and tombs, yet their meaning was locked away, an entire culture rendered mute by the passage of time. Then, in 1799, a seemingly ordinary slab of granodiorite was unearthed near the Egyptian town of Rashid, or Rosetta. This was the Rosetta Stone, and its discovery would ignite a scholarly race that captivated Europe. The brilliance of Jean-François Champollion, a French philologist, lay not merely in his prodigious linguistic talent, but in his revolutionary insight into the very nature of language. He spent years obsessively studying the stone, which bore the same decree inscribed in 3 scripts: hieroglyphic, demotic, and ancient Greek. Scholars had made little headway for decades, viewing hieroglyphs as purely symbolic pictograms. Champollion, however, began to meticulously compare the texts, driven by a hunch that had eluded others. He theorized that the hieroglyphs were not solely ideograms, pictures representing ideas, but a complex blend of phonetic elements, where symbols represented sounds, alongside logographic or symbolic elements, and even deterministic signs that clarified the meaning of a word. It was this understanding, this recognition of language as a layered system, that allowed him to unlock the secrets of ancient Egypt, revealing not just words, but the very grammar and thought processes of a civilization separated from his own by millennia. His triumph was the ultimate Rosetta Stone, a bridge across a vast cultural and temporal chasm. Now, extend that challenge across light years, across the infinite gulf between species. How do we build a bridge when there's no shared historical text, no common biology, no mutual understanding of even the simplest cultural nuance? In 1960, the very same year Frank Drake initiated Project Ozma, a visionary Dutch mathematician named Hans Freudenthal tackled this seemingly insurmountable problem. His solution was Linkos, short for lingua cosmica, the first language constructed explicitly for interstellar communication, designed to be understood by any intelligence capable of rudimentary logic and mathematics. It was a pioneering work, largely forgotten by the public, but foundational to the philosophy of interspecies communication. Freudenthal's genius was to build Linkos from first principles, starting with concepts so universal they transcend any specific biology or culture. He envisioned a message composed of simple radio pulses, sent in varying patterns and durations. A single pulse followed by a pause, then 2 pulses, then 3, then 4, could immediately begin to teach the concept of numbers. 1, 2, 3, 4. From there, simple arithmetic could be introduced, a pattern for 2 pulses plus 3 pulses equals 5 pulses. Equations like 2 plus 3 equals 5 become undeniable truths for any mind that comprehends quantity. From basic arithmetic, the language could then escalate, step by careful step. Concepts of equality, inequality, and variables would follow, establishing the bedrock of logic. Imagine a sequence of pulses that teaches time, using the fundamental frequency of hydrogen, the most abundant element in the universe, as a universal clock. Imagine further how Linkos could then progress to explain concepts like distance, mass, and even the fundamental laws of physics and chemistry, all through carefully constructed sequences of radio pulses. But Linkos dared to go further still. Freudenthal theorized how, once the physical and mathematical foundations were laid, one could begin to introduce concepts of behavior, of consciousness, and even of emotion. It's a breathtaking thought. Teaching the meaning of joy or sorrow to a species with whom we share absolutely no evolutionary history, using only the cold, hard logic of mathematics as our common ground. Linkos is not just a theoretical construct, it is a profound philosophical statement. It asks whether universal concepts, deeply rooted in the unchanging laws of physics and mathematics, can truly serve as the ultimate cosmic Rosetta Stone. Can these shared truths of the universe allow any two intelligent species, no matter how disparate their origins or their forms, to bridge the seemingly infinite gap of biology and culture, to truly understand each other? The quest to decipher an alien message is, at its heart, a quest to understand if universal reason is enough to forge a dialogue across the void. For decades, humanity has aimed its powerful gaze at the distant stars, listening for a whisper in the cosmic void, hoping to decipher a message from an alien civilization. Yet, a profoundly humbling truth lies not billions of light years away, but just beneath the shimmering surface of our own blue planet. Before we ever hope to decode the intentions of an extraterrestrial mind, perhaps we must first confront the immense and often perplexing challenges of communicating with other intelligent beings that already share our world. These are not visitors from other galaxies, but highly complex, non-human minds residing in the deep oceans right here on Earth. Among these extraordinary terrestrial intelligences, the bottlenose dolphin stands out, possessing a brain that, in some fundamental aspects, is larger and arguably more intricate than our own. Their cerebral cortex is highly folded, a characteristic often associated with advanced cognitive abilities, mirroring the complex neural architecture found in human brains. This remarkable neurological development has captivated scientists for generations, leading to questions about the nature of their thoughts, their social structures, and most importantly, their unique forms of communication. It compels us to ask, if we struggle to understand the intelligence swimming in our own waters, how can we expect to grasp the language of a species from another star system? To bridge this immense cognitive chasm, researchers like Dr. Denise Herzing have dedicated decades of their lives to what is known as the Wild Dolphin Project. Her mission, a testament to unwavering scientific curiosity, has been to establish a genuine two-way communication bridge with these remarkable marine mammals in their natural habitat off the coast of the Bahamas. This isn't about teaching dolphins human tricks. It's a sincere, methodical effort to understand their intricate world and to allow them to communicate back to us on their own terms, using technology designed specifically to interact with their unique sensory perceptions. The cutting-edge science of dolphin communication reveals a tapestry far richer than simple clicks and whistles. While these vocalizations are certainly a part of their acoustic repertoire, they are merely one layer of a complex interplay that includes sophisticated body language, intricate social maneuvers, and perhaps most astonishingly, an advanced form of sonar imaging. Dolphins use echolocation not just to navigate or hunt, but potentially to create what some researchers describe as holographic, like sonic packets of information. Imagine a sound that isn't just a wave, but a detailed three-dimensional picture transmitted directly into the auditory cortex of another dolphin, allowing them to share an immediate, sensory-rich understanding of their environment. We are only just beginning to comprehend the profound implications of such a communication system. A deeper look into the architecture of a dolphin's brain, particularly its highly developed paralimbic system, suggests a fundamental divergence from human cognition. While our human intelligence often excels at tool-based reasoning and object-oriented manipulation of the physical world, the dolphin brain appears to be profoundly geared towards emotional processing, social bonding, and complex relational dynamics. Their world is one of fluid motion, shared experience, and an intimate understanding of each other's inner states, perhaps more so than our own. This difference challenges our anthropocentric biases, forcing us to consider that intelligence can manifest in forms completely alien to our own, prioritizing aspects of existence that we, as a species, might undervalue or simply fail to recognize. This journey into the minds of our terrestrial aliens serves as a critical cautionary tale for the ambitious search for extraterrestrial intelligence. It vividly demonstrates that, even with a shared planet, a common biology rooted in Earth's chemistry, and a profoundly similar environment, the gap between two intelligent species can be immense, filled with assumptions and misunderstandings. The struggle to recognize and interpret the rich language of dolphins highlights a profound limitation in our search for alien signals. The celebrated great silence that pervades the cosmos, the absence of detectable alien broadcasts, might not be due to a lack of signals at all. Instead, it could be a testament to our profound inability to recognize a form of communication that simply does not fit our narrow, human-centric definition of what a language should sound or look like. We may be listening for a radio signal, while across the universe, an intelligence communicates through something we are yet to conceive. For decades, the silence of the cosmos has resonated with a single, profound question, famously posed by Enrico Fermi: where is everybody? It is a question that gnaws at the very core of our cosmic isolation, driving speculation from the apocalyptic to the fantastical. We have searched for signals, pondered alien languages, and even considered the possibility of intelligences vastly different from our own. But what if the answer isn't about their will or their desire to communicate, but something far more fundamental, something rooted in the universal laws of economics and thermodynamics? This is not a philosophical riddle, but a practical inquiry into the very viability of a galaxy-spanning civilization. Could such an empire, stretching across hundreds of thousands of light-years, even be an economically or energetically sustainable enterprise? To seek understanding, we must turn our gaze from the distant stars to the intricate, often brutal realities that govern growth and decay right here on Earth. Consider the groundbreaking work of physicist Geoffrey West, a pioneer in complexity science. His research has unveiled startling universal scaling laws that dictate the life cycles of nearly all complex systems, from the intricate metabolic rates of biological organisms to the sprawling infrastructure of our largest cities and the relentless rise and fall of global corporations. These laws suggest that all complex systems, regardless of their nature, eventually confront a critical point of diminishing returns, leading inevitably to stagnation or even complete collapse. As a city grows, for instance, its infrastructure costs do not scale linearly with population. They grow at a disproportionately faster rate, demanding ever more resources and energy just to maintain existing functions, let alone expand. Now, extend this principle to a hypothetical civilization embarking on interstellar colonization. The energy and resource costs associated with building faster than light drives, or even slower, generation ships capable of traversing the immense voids between star systems would likely grow exponentially with each new star system added to the network. Sending just one small probe to a nearby star like Proxima Centauri, a mere 4.2 light-years away, would require energy levels many orders of magnitude beyond anything humanity currently commands, equivalent to the entire annual energy output of a major industrialized nation. Scale that up to colonizing hundreds, thousands, or even millions of star systems across a galaxy 100,000 light-years wide, containing hundreds of billions of stars. The financial and energetic burden would become astronomically, perhaps even infinitely, unsustainable. Yet, the benefits of such expansion, the acquisition of new planets or resources, would likely remain linear, a one-for-one gain, failing to match the ever-escalating costs. This creates an insurmountable economic barrier, a fiscal wall that could act as its own great filter, preventing any civilization from truly expanding across the galactic disk. Perhaps, then, the ultimate sign of true intelligence and the true triumph of civilization is not unbounded expansion, but profound self-restraint. We explore the concept of homeostasis on a cosmic scale, suggesting that a truly advanced, long-lived civilization would prioritize sustainability, efficiency, and perhaps most importantly, virtual exploration over costly, physically demanding expansion. Why send an expensive, resource-intensive generation ship across dozens of light-years to a new star system when a perfectly simulated, entirely digital universe could offer infinite possibilities, all without the immense energetic drain of physical travel? Such a civilization would become virtually invisible. They would not build massive, energy-intensive Dyson spheres to harness entire stars, leaving detectable technosignatures across the cosmos. Instead, they might optimize their energy use to near-perfect efficiency, recycling every joule, leaving a footprint so minuscule it becomes indistinguishable from background cosmic noise. Their expansion might occur within the confines of their home system, or even within the digital realms of their own minds, exploring mathematical constructs or simulated realities of breathtaking complexity. This economic perspective fundamentally overturns the traditional interpretation of the Fermi Paradox. The silence we observe in the cosmos might not be a desolate sign of absence, a galaxy devoid of life, but rather a profound indicator of widespread intelligence, a universe where sustainable economics and the preservation of resources have triumphed over the primitive, self-destructive impulse for infinite physical growth. The cosmic silence, once perceived as an empty canvas, is now understood as a torrent of information, a digital deluge that far exceeds human capacity to process. For decades, the search for extraterrestrial intelligence, or SETI, was largely the domain of a few dedicated astronomers, patiently scanning the skies with their radio telescopes. Their efforts, though pioneering, generated data volumes that were, by today's standards, quaint. But the modern era has fundamentally transformed this quest, catapulting it from a niche scientific pursuit into an immense, global, big data problem, one that only the burgeoning power of artificial intelligence can hope to tackle. To comprehend the scale of this transformation, consider the colossal undertaking known as the Breakthrough Listen initiative. This ambitious program, funded by a visionary philanthropic commitment, now generates more raw data in a single day than all previous SETI projects combined throughout history. This is not merely a quantitative leap, it is a qualitative shift, creating an analytical challenge so vast it would be utterly impossible for human minds to sift through. One could spend 1,000 lifetimes examining just a fraction of the signals collected, searching for a single pattern, a faint whisper from across the void. At the heart of this technological revolution stands a figure like Dr. Jill Tarter, a trailblazer who has dedicated her life to the search. Her tireless advocacy and foresight were instrumental in recognizing that the traditional methods of human-driven analysis were simply unsustainable in the face of this ever-growing cosmic data stream. This realization spurred the development of increasingly sophisticated machine learning algorithms designed to become the ultimate cosmic listeners, capable of discerning patterns and anomalies hidden within terabytes upon terabytes of seemingly random noise. These advanced artificial intelligence systems are not merely trained to identify simple, repeating signals, the kind one might expect from a basic beacon. Their programming goes far deeper, enabling them to hunt for complex, information-rich modulations, intricate variations in frequency, amplitude, or phase that could encode vast amounts of data, akin to a cosmic broadcast. Furthermore, these algorithms are specifically designed to detect anomalous technosignatures that defy natural explanation. Picture the heat signature of a Dyson sphere, a hypothetical megastructure built by an advanced civilization to completely enclose a star and harness its entire energy output, radiating a unique infrared glow unlike any known stellar phenomenon. Or consider the atmospheric pollution of an industrial civilization on a distant exoplanet, detectable as unexpected chemical compositions in its spectral signature, a telltale sign of intelligent activity altering its environment on a planetary scale. These are the subtle, yet profound, clues that artificial intelligence is now meticulously searching for. When one of these AI systems flags something unusual, it doesn't immediately trigger a global announcement. Instead, it enters a rigorous, multi-layered verification process. Initially, the AI might identify a signal of interest, an intriguing anomaly that warrants further investigation. This is distinct from a candidate signal, which represents a much higher level of confidence. To elevate a signal from mere interest to a true candidate, it must undergo extensive scrutiny. This involves cross-referencing against vast satellite databases to rule out terrestrial interference, checking astronomical catalogs to ensure it is not a known natural astrophysical phenomenon, and critically, initiating follow-up observations from multiple independent observatories across the globe. Only if all these checks clear, and the signal persists and cannot be explained by any known natural or human-made source, does it become a true candidate for extraterrestrial intelligence. This meticulous, technologically driven approach demonstrates that the modern search is no longer a passive waiting game, a hopeful scan of the heavens. It has evolved into an active, aggressive hunt, an ongoing digital dragnet cast across the cosmos. The new frontier of discovery is not solely about building bigger and more powerful telescopes, though these remain vital tools. Instead, the real breakthroughs now lie in writing smarter code, in refining the algorithms, and in training the artificial intelligences that tirelessly sift through the digital deluge of the cosmos, listening for that one profound whisper that could change everything we know about our place in the universe. For decades, humanity has peered into the cosmic void, straining to hear the faintest whisper from an alien civilization. We have built colossal telescopes, developed sophisticated algorithms, and trained artificial intelligences to listen with unparalleled precision. Yet, a question rarely explored in popular imagination remains. What truly happens the moment that whisper becomes a confirmed message? What unfolds in the sober, real world, far removed from the explosive narratives of Hollywood, when humanity finally makes contact? The answer lies within a remarkable yet largely unknown framework: the Declaration of Principles concerning activities following the detection of extraterrestrial intelligence, more commonly known as the SETI post-detection protocols. These aren't just theoretical musings. They represent a cautious, meticulously planned blueprint for humanity's most profound encounter. Their genesis stretches back to the 1980s, when a small group of scientists, driven by both hope and an immense sense of responsibility, began to contemplate the unthinkable. They understood that such an event would be less about spaceships landing on the White House lawn and more about the delicate, complex management of information on an unprecedented global scale. Today, these protocols are overseen by a complex web of esteemed scientific bodies, including the International Academy of Astronautics, or IAA, and the Committee on Space Research, known as COSPAR. These organizations bring together astronomers, physicists, sociologists, and policymakers from dozens of nations, all working to establish a shared, rational approach to an event that would redefine our place in the universe. It is crucial to understand, however, that despite their meticulous detail and broad scientific consensus, these protocols currently lack any binding legal force under international law. They are, in essence, a gentleman's agreement among the global scientific community, a set of guidelines designed to ensure a measured, responsible response should the unimaginable occur. So, how would it unfold? The first, paramount step is rigorous verification of the signal. A potential detection, however compelling, must be confirmed by at least one, and ideally multiple, independent observatories using different instruments. This painstaking process, which could take days, weeks, or even longer, is designed to eliminate every conceivable terrestrial source, from rogue satellites to misidentified natural astrophysical phenomena. Only after this multi-layered confirmation, a gauntlet of scientific skepticism, would the signal be deemed a true candidate for extraterrestrial intelligence. Once verified, the information would then enter a phase of confidential notification. This isn't about secrecy for secrecy's sake, but about preventing panic and ensuring responsible dissemination. Other observatories, select national governments, and key international bodies like the United Nations would be quietly informed. This measured approach allows time for strategic planning and coordination before the weight of the news crashes down upon the global public. Finally, and with immense caution, a carefully managed public announcement would be made, designed to provide accurate, credible information, preventing the spread of misinformation in an instant-sharing world. One of the most crucial and indeed controversial aspects of these protocols is their strong recommendation against immediately sending a reply. This principle is born from a deep-seated caution, a fundamental recognition of the profound unknowns inherent in such a contact. Revealing our precise location, our technological capabilities, or the very nature of our civilization to an unknown intelligence carries risks that are simply too immense to rush into. What if the signal comes from a civilization with intentions we cannot comprehend, or capabilities far exceeding our own? This non-response clause is a silent testament to humility and self-preservation in the face of the truly alien. To grasp the potential societal impact of such a moment, we can turn to the insightful work of social scientists like Albert A. Harrison. His studies have meticulously catalogued the myriad ways humanity might react to confirmed contact, from widespread euphoria to profound existential dread, from global unity to fragmentation. We need only look to historical precedents to understand this volatile dynamic. Consider the infamous Orson Welles' War of the Worlds broadcast in 1938. A fictional radio drama, presented with jarring realism, triggered widespread panic across parts of the United States, convincing hundreds of thousands that an alien invasion was truly underway. This historical event, driven by powerful narrative and a lack of credible official counter-information, serves as a stark reminder of humanity's susceptibility to fear and misinformation. In our current era of global social media, where a single tweet can circle the globe in milliseconds, the psychological need for official, credible information following a confirmed signal would be paramount. Without it, the vacuum would be instantly filled by speculation, conspiracy theories, and potentially dangerous narratives. The protocols, therefore, are not just about receiving a message. They are about managing humanity's deepest hopes and fears, about steering our collective consciousness through an event that would rewrite our understanding of everything. The very act of planning for contact forces us to confront our own fragility, our biases, and our profound need for truth in a universe that remains largely unknown. The cosmos, in its silent, unfathomable expanse, holds a question that has haunted humanity for centuries. Are we alone? For some, the search for extraterrestrial intelligence, or SETI, is a grand cosmic lottery, a quest for the definitive proof that we are but one voice in a galactic choir. But what if the profoundest truth of this endeavor lies not in the discovery of an alien signal, but in the very act of searching itself? What if SETI is less about finding them and more about truly understanding us? Our journey into the void began with a humbling realization. The universe is not just filled with distant stars, but with the omnipresent hum of our own technological civilization. The initial challenge was to discern a true message from the cacophony of our own making, a lesson learned firsthand from declassified moments where seemingly alien pulses turned out to be echoes of our own terrestrial ingenuity. This fundamental problem forced us to confront the very nature of what constitutes a signal, pushing us to define the boundaries between natural phenomena and intelligent design, a definition that constantly evolves with our own technological advancements. We learned that to listen for others, we must first truly understand the noise we ourselves generate. Then came the deeper, perhaps even more daunting question. If we did receive a message, how could we possibly decode a language born from a biology and history utterly alien to our own? We have grappled with the decipherment of ancient Earth scripts, like the Rosetta Stone unlocking Egyptian hieroglyphs, a triumph that required not just a key, but a revolutionary understanding of language itself as a layered, structured system. Extend that intellectual Everest across light years, and the challenge multiplies beyond measure. Consider the audacious attempt to construct a universal language, lingua cosmica, built from the most fundamental laws of mathematics and physics, a testament to humanity's belief that universal reason could bridge any gap. This pursuit of cosmic communication pushes the boundaries of our own linguistics, forcing us to explore the very essence of how meaning is created and shared, even across unimaginable divides. Yet, before casting our gaze to distant star systems, a profound lesson awaited us in the shimmering depths of our own oceans. We explored the humbling complexities of attempting two-way communication with bottlenose dolphins, minds that share our planet, yet possess a cognitive architecture vastly different from our own, potentially geared towards emotional and social processing rather than our tool-based intelligence. This interaction with terrestrial aliens reveals the immense anthropocentric biases we carry. Our definitions of intelligence, consciousness, and communication are deeply rooted in our human experience. The silence we perceive in the cosmos might not signify an absence of other intelligent life, but rather our own profound inability to recognize forms of communication that transcend our narrow, human-centric expectations. The famous Fermi Paradox, that persistent query of "where is everybody, Gav?" takes on a new dimension when viewed through the lens of economics and thermodynamics. Could a galaxy-spanning civilization truly be a sustainable enterprise? The universal scaling laws observed in everything from biological organisms to cities suggest that growth inevitably hits diminishing returns, with energy and resource costs potentially escalating exponentially, while benefits remain linear. This economic perspective suggests that the Great Silence might not be a sign of absence, but a profound indicator of widespread intelligence, civilizations that have prioritized sustainable existence and cosmic introversion over costly physical expansion. Perhaps the true mark of an advanced society is not boundless outward reach, but rather a mastery of internal efficiency and virtual exploration, rendering them virtually invisible to us, simply because their existence does not conform to our primitive drive for infinite material growth. In our own time, the search has transformed from dedicated astronomers patiently scanning the skies into a monumental big data problem, tackled by the relentless processing power of artificial intelligence. Projects like Breakthrough Listen generate more data in a single day than all previous SETI efforts combined, a deluge that only sophisticated machine learning algorithms can hope to sift through. These AI systems, trained to hunt for complex modulations and anomalous technosignatures like the heat signature of a Dyson sphere or the atmospheric pollution of an industrial civilization, are reflections of our own rapidly advancing technological prowess. The very tools we build to listen to the void are themselves a testament to our intelligence, our ingenuity, and our evolving capacity to perceive the universe in new ways. And should that monumental moment arrive, should a confirmed signal pierce the cosmic silence, what then? We explored the carefully crafted yet legally non-binding SETI post-detection protocols. These guidelines, born from decades of cautious foresight, reveal our collective fears and hopes, a rigorous verification process, confidential notification of governments and the United Nations, and the controversial recommendation against immediate reply, a principle rooted in profound caution about revealing ourselves to the unknown. Our societal preparedness, or lack thereof, for such a paradigm-shifting event forces us to confront our own capacity for collective action, for managing global information in an era of instant and often misinformed communication, drawing lessons from historical incidents like Orson Welles' War of the Worlds broadcast. Ultimately, the search for extraterrestrial intelligence is far more than an astronomical endeavor. It is a profound journey of self-discovery. It forces us to confront the limits of our own perception, the biases inherent in our understanding of intelligence, and the fundamental laws that govern the growth and longevity of any technological civilization. The Fermi Paradox, then, is not merely a question about aliens. It is a mirror reflecting our own trajectory, our own potential for long-term survival, and our place in the grand tapestry of existence. By listening to the cosmos, we are compelled to listen to ourselves, to examine our progress, our limitations, and our deepest aspirations. The act of searching, regardless of its ultimate outcome, stands as one of humanity's most ambitious, humbling, and profoundly worthwhile scientific and philosophical undertakings.